Hey folks, in this video, I'm going to show you the relationship between the area of a parallelogram and the determinant of a 2x2 matrix, right? So we saw in class that the area of a parallelogram can be found by calculating this determinant, but it wasn't so clear as to why that connection held. So I'm going to set this up. You'll notice that I have a parallelogram drawn already. It's defined by the two vectors u and v. So u is the column vector AC, V is the column vector BD. So if I make a matrix whose columns are given by U and V, I'll get the matrix A, B, C, D, right? So in order to calculate the area of this parallelogram, I'm going to do a little geometric proof. And so you'll notice I already drew some rectangles on the figure here. And so the first thing I want to do is figure out what are the dimensions of these rectangles. So let's start with the larger rectangle that comes from the origin. What's the width of this rectangle? Well, you'll see that it goes all the way out to the same width of the u vector. In other words, the x1 component of the u vector. So how far across is this? Well, it is now a units across. What about the height of this rectangle? Well, the height should be the same as the height of my v vector, which is the x2 component of my v vector, that's d up. So I'm a units across, d units up. What about the smaller of the two rectangles, right? The one in the upper right corner of my diagram. Well, to figure out the width of this rectangle, you'll notice that it's the same as the width of this vector. But because this is a parallelogram, this vector that I'm highlighting is exactly the same vector v, just shifted. So how far across does the v vector go? Well, it goes b units across because that's the x1 component. So this is b units across. And using a similar idea, the height of this rectangle is the height of this vector. But this vector is simply the u vector shifted. And so the height of the u vector is c, which means my rectangle has height c. Wonderful. So now, in order to find the area of the parallelogram, what I'm going to do is actually take the diagram take the parallelogram you see, try to cut it up into pieces and fit them into the original AD box, okay? So here, I'll start with this piece here. So I'm going to actually trace it out with my pen. If I did an okay job, okay, I did an okay job. So I'm going to make this, sort of a slightly darker blue, just so we kind of remember where it came from. And so this piece of the parallelogram, I'm going to drag and put it right here. Yeah, you see, it's just like a perfect little match right there. Wonderful. Okay. Now, what did I miss? I missed this little segment of the parallelogram. So I also need to cut this up. Oh, didn't want to make that little area for me. Try it one more time. So I also want to turn this into a little shape. There it goes. And now I'm going to drag this over here. Again, perfect little fit. Ooh. There we go. So in other words, right, what we figured out so far is that the area of the parallelogram, well, it's almost A times D, right? Because A times D is the area of the rectangle. But of course, all of you will see that I've actually missed two regions, right? And so I haven't really filled up the entire rectangle AD. So I need to subtract some amount. And the question is, how much do I need to subtract? Okay. Well, luckily for us, if I go back to that little rectangle BC, you might recognize that some of the shapes that are in there are going to correspond really well to the missing spots in the AD rectangle. So namely, if I draw this little rectangle, or sorry, this little triangle here, I'm going to change this to pink, then this little triangle fits perfectly in this spot. And what about the sort of trapezoid in the upper corner of the AD rectangle? Well, if I draw this shape, this trapezoid, I actually have to try to trick Notability because it doesn't like drawing trapezoids for me. Okay. But that shape right there, if I drag this over, again, it's a perfect fit. And so the question mark area, right, is exactly the area of these two pink shapes. And how much is this? Well, if I put them back, you'll see that they exactly fill the BC rectangle. And so in other words, the area of the parallelogram is AD minus the area of the little rectangle, which is BC. But that, folks, is exactly the determinant of the matrix ABCD. So I hope this geometric argument helped you see why there was a connection between determinants and area of parallelograms. If you have any questions, please don't hesitate to reach out.